Hello, welcome to Whiteboard Learning. Today we're going to talk about sodium disorders. And you may remember we talked in membranes and gradients and fluids introduction about why sodium is so important. I thought we'd just quickly remind ourselves of that. So your body is full of a lot of salts, and sodium salts are one of the most important. And then you have potassium salts as well. They can also, other than pairing up with chloride, remember this is the sodium symbol, and this is the chloride symbol, and that's the potassium symbol when you talk about it elementally. And they can pair up with other things, so sodium bicarb, sodium in sort of a citrate or a phosphate. There's all kinds of different sodium compounds. But sodium and chloride in the body are very, very they're partners. They like to be where each other are. And what happens in the body is that sodium, like many other salt type materials, elements, gets broken up so that the sodium is by itself and the chloride breaks off. And why it does that is because water comes along. So oxygen with two hydrogens. Oh no, I went all high school chemistry with you. So the important thing is that this is the positive end of this, and this is the negative end of this, and that's attracted to the positive. So a sodium will get taken away from its chloride by water with all these charges. And then the other side is that these hydrogens like to hang out with the chloride. So sodium and water in the body break up sodium chloride, and then sodium and water are best friends. And water and sodium, since they like to be around each other, water tends to go where sodium is because sodium is very restricted. So remember that the blood vessel is here, and then you have cells here, and then this is the interstitial fluid. Remember we talked about that. And so this milieu in here is mainly potassium, and then out here is mainly sodium. As far as the major cation or positively charged item. But that doesn't mean that the saltiness of the fluid is different. So the saltiness of this fluid out here is 300, and the saltiness of this fluid is 300, and that's milliequivalents per liter, right? We talk about sodium and potassium and chloride as milliequivalents per liter. And this is what we call the osmolarity, or the saltiness of the solution is 300. Well, it's about 310, 330, but easiest to remember it as 300. Now, how does it do that? Well, there's a calculation for that. So you can say that the saltiness of the blood and interstitial fluid is based on 2 times sodium plus potassium, basically. So that's about 140 plus 4, so that's 144, and 2 times 144 is 288. So there's a little bit missing, and the rest of that equation is generally a little bit of sugar and a little bit of urea, or if you think about that as BUN. But those to a lesser degree. Mostly it's the sodium and potassium, of which mostly in the extracellular fluid is sodium. And so that's why sodium is so important for how do we deal with the saltiness or the components of this extracellular fluid, because it's one of the most important things. And why is osmolality important? Because it controls where the water goes, which is really important for cell size, because water here inside the cell, because this is not a plant cell, it's an animal cell, so it's not rigid. Water here will want to move here if this suddenly becomes 400. Remember, water wants to go where the higher salt is, and so it will go out here and the cell will shrink. So let's do that sort of in a separate, situation. Let's take a red blood cell in the bloodstream. So here's a red blood cell sitting in the bloodstream, and that has 300 osmolarity inside the cell, and there's 300 out here. Well, if I suddenly make this 400, of mostly adding salt, because that's the easiest way to increase it to 400, there's just a certain amount of water in here, and that water will say, well, no, this needs to be 350 on both sides so they can be equal. Water will diffuse freely across that membrane, and that will make this cell shrink. So this cell will no longer be so big, but it will now have matching salt inside and outside, or osmolarity, even if it's made up of other components, not salt. It'll still be that way, because you remember inside cells, potassium's actually 140. So if I were going to calculate the osmolarity inside the cell, that 2 times sodium plus potassium would actually be different. This would be the 140, and this would be like the 10. So it doesn't really matter what salt it is. It really matters relative to water, how salty it is. I hope that makes sense. But basically, when you add salt out here, it makes the cell shrink because water wants to dilute out the higher concentration of the salt here. The same would be true if you added another type of salt, but generally that would kill you before it would make the change. So if you add a lot of potassium, to someone's blood, it would kill them because potassium is bad for your heart way before it would change your cell size. So how is this important in sodium disorders that this happens? Well, the same thing would happen everywhere in your body. And so it's important to think of what cells, their size really matters. Well, a muscle cell, if it got bigger or littler, it might not work quite as well, depending on where fluid is moving. But the one place that this matters the most is in cells that don't have the ability to expand or contract very easily or handle it. And this is really in your brain. Your red blood cells are one, and then your brain. So the brain being stuck in your skull, here's your little brain, put a little cerebellum in there, a little brain, a little division in the middle. Your brain is stuck in this bone. And so if it tries to expand or contract, it really has a hard time. And so if it contracted, that would open up a space, and that space would fill with blood. And then you would have a problem, obviously, with hemorrhage, and your brain would not function very well. Or if the brain tried to expand, it would expand all the way, and you'd have brain swelling, and you could herniate the brain out of one of the places, like in the skull. If you're looking at a skull curve this way with teeth, I'm a very bad artist, you know that. Then the brain here could herniate out here if it's swollen too much. And that you hear a lot about head trauma. Why patients die is from brain swelling, but that has nothing to do with sodium. So let's talk about hypernatremia and hyponatremia and why that is a problem. So let's talk about hypernatremia. So that is when your blood sodium is too high. Hyponatremia is when your blood sodium is too low. That makes sense, right? Hyper and hypo. Let's remind ourselves of what is normal. So normal sodium is about 140 to 145, depending on the scale and depending on the species. So that's milliequivalents per liter. Now, what happens in hypernatremia? Well, if it happens very suddenly, that's actually more of a problem with both of them than if it happens slowly. And so we'll talk about why slowly is a little bit easier. But let's say you suddenly put in hypertonic saline. Well, that saline is much higher, and it's about 2,000 milliequivalents per liter, whereas regular fluids are still about 140 on the sodium. So what if I also ate salt? Or what if I ate Play-Doh? That's got a lot of salt in it. What if some paint gun pellets have salt in them? What if I ate salt water? So if I did any of those things and suddenly shot my blood sodium up from the 140 to, let's say, 200, what would happen to my brain? So let's do a little brain cell here, and here's the bloodstream going by. So inside, the osmolarity in here is about 300. And if I suddenly made the osmolarity outside about 350 or 60, let's say, from its normal 300, right? So what's going to happen here? The water inside the cell is going to be attracted to the higher concentration here. And so it's going to leave the cell. The cell will shrink. So let's draw a smaller cell inside the brain. That's when the bleeding will happen inside the skull. And then this will be about 320, and this will be about 320, somewhere around there. So now you have a patient who will be obtunded or seizing, or maybe in a coma as well, which is kind of obtunded but worse, or dead, because they'll have all this bleeding. The other thing that can happen to this patient is, let's say this only happened a little bit, but I go to correct this sodium problem and I put in a low sodium fluid. So now I put in a water type fluid like dextrose 5 water, and I suddenly bring down the osmolarity of the blood down to 270. And this is 320. What's going to happen now? Well, instead of this, if I do this very suddenly, now water, because there's extra water here, this is a much more watery solution, is going to go back in. And this is going to swell very quickly. And that's the same situation that would happen with hyponatremia if I suddenly drank fresh water, or I gave a bolus of a water solution like dextrose, 5% dextrose in water. That would suddenly bring this down to, what if I brought it down to like 100? And so if I do that suddenly, all the extra water rushes into the cell and makes it swell. So like with red blood cells, that would make them swell and they might burst because their cell membranes are not strong enough. And if I do that to a brain cell inside the skull, my little brain now is swollen, it might herniate, and I would have the same seizures or problems like that. So sudden changes in sodium are mostly bad for your red blood cells and your brain. What's interesting, if it's not sudden, is that you can have an adaptation. So let's say the most common thing that can happen with sodium is that I am a kidney cat. And a kidney cat, that's a little kitty who has bad kidney disease. The thing that happens to them is that their kidneys tend to lose free water. So they lose water more than they gain, right? Maybe they can't drink enough for how much they're losing because they're polyuric and polydipsic, but they can't drink enough. But they also aren't losing sodium as fast as they are losing water. So this is lower than the losing of water. So overall, their sodium might have started at 145, and then it'll creep up to 155, and that'll be 165, and 175. These guys will be chronically hypernatremic. Now, why aren't they having trouble with their brain? Well, what's interesting about cells that are in a chronically salty environment is that they are very smart. So here's my cell, and it's noticing that there's an increasing osmolarity out here. Sorry for the barking dog. And it'll sense that it's starting to get a little bit smaller. And it says, that's not good. I need to maintain my size. I don't want to lose so much water all the time. And so if it happens slowly over like 3 to 5 days, it makes what's called organic osmolytes. And these are proteins made by the cell. They used to be called idiogenic osmoles, but they changed the name. The cell will start to make them, and these are proteins now, and that'll hold on to water, and that water will stay in the cell even if this is staying high and trying to draw water out. They'll make these proteins and it'll hold. What is the problem though is if I chronically become hypernatremic and my body adapts, then I will have these things in. So if a doctor comes along and says, oh my goodness, that cat's sodium is 175, let's give it D5W, and give that as its main fluid, I got to get that sodium down. And so there's extra water here that wants to move into that cell. That cell is going to get big very fast because it didn't make these proteins very suddenly. It made them over time, and so it can't get rid of them when it's sensing a dropping of the osmolarity. It can't get rid of them quickly. It has to slowly metabolize them in response to it. So that's one of the things about treatment of sodium disorders, is if it happens quickly, you can treat it quickly. If it happens chronically, you have to be very careful and treat it chronically. You have to treat it over a few days. You don't want to change it more than maybe 5 to 10 milliequivalent per day so that you don't get sudden changes because the cell has adapted to the chronic saltiness of the blood. So those are some just main points about hypernatremia and hyponatremia. The main patients that become hypernatremic and hyponatremic are somewhat the same category. They can be cats with renal failure, dogs with renal failure. About 10% are hypernatremic, but mostly are hyponatremic. They're losing more sodium than water from their kidneys. They're also potentially not taking in enough, but some are the opposite. And there are some, that are also normal with their sodium as well. But as far as the ones that have messed up sodiums, the other ones are diabetics. So diabetics or diabetic ketoacidotics. Most of them, if they're going to have a sodium problem, have a low sodium, but some are hypernatremic. And those are the most common chronic diseases. You can also think of Addison's, right? Addison's disease has a high potassium but a low sodium. So you have to be careful with how low they have gone because they've probably gotten there chronically. And those are some diseases that we have to be careful treating. So I hope that helps. There's also going to be a short video on how to do the treatment and how to measure the effect of fluids in that. That's going to be a separate video, so you can watch out for that. All right, thank you.